Okay, so taking a look at AP Physics Vertical Motion Problem 2. You drop a stone into a deep well. If it takes 2.5 seconds for you to hear the splash, how deep is the surface of the water? Assume the speed of sound is 343 meters per second. And that's the time for that echo to come back up, right? The speed at which the echo is coming back up, 343 meters per second. I'm going to assume that's constant speed. So this problem, I hope, sounds familiar to you. I think it was, you did a similar problem in honors physics last year, where we were dropping a stone off a cliff in Waimea Canyon in Hawaii on Kauai, on the island of Kauai. Anyway, we did a similar problem last year. So hopefully this first part's pretty straightforward, but then we didn't ask about parts B and especially C last year in honors because, well, frankly, a little bit more calculation than we really need to get into. Part B is interesting. Part C is just a little brutal. But anyway, here we go. So I have the solution already written out here. I'm just going to go ahead and work off that. So start with, here's my sketch. All right. So I have stone being dropped, going faster, 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 sploosh, and then the echo is going to come up at nice, really fast, but constant speed, right? The splash sound. We're going to call the depth here of the well. I'm just going to say that the magnitude of that is a positive h. Okay, we're going to go down negative h and back up positive h. We're going to call that magnitude of that depth h though. So the first thing I'm going to do is I'm going to think about the time it takes for this rock to fall and the sound to come up. That total time is 2.5 seconds. That's going to be a combination of 2 times, the time for the fall and the time for the sound to come up. So I'm going to say that the total time is the time for the rock to fall plus the time for the sound. I can go ahead and say I know the total time is 2.5 seconds. So 2.5 equals TF plus TS. And that gives me an equation to work with. Again, I'm not working from a formula here. This is just a relationship that we are supposed to spot ourselves between those 2 times. Now getting to equations, this time for the rock to fall, can we model that? And you say, well, sure. I'm going to go ahead. I know a displacement here. I'm going to call h. That's what I'm trying to find, which is negative h going down, but whatever. We know the initial velocity is 0, and we know the time is this tf. And the acceleration we know is going to be negative g, right, going down. So I can go ahead and, for the rock falling, use this delta x is v naught t plus 1 half at squared formula. I'm going to go ahead and say v naught is 0 because it's dropped. Technically, it's going down a negative h, and the acceleration is negative g. Remember, little g stands for positive 9.8 near the surface of the Earth. The gravitational field strength or acceleration due to gravity. But if someone asked me what's the acceleration of this falling object, I would say it's negative g. So there's a negative there and a negative there that canceled out. I didn't show that, but technically I'm canceling a negative sign on both. And that gives me this nice equation. When I plug in 9.8 for g, I get that h is 4.9 t time for the fall squared. Okay. You say, now what about the sound coming up? Well, the sound, we're going to presume that is going at a constant speed. And so the time for the sound, again, if I use that same formula, v naught t plus 1 half at squared, but the acceleration is 0 because we're going at constant speed. So that term is going to drop. So I just have delta x is v naught t, but the velocity of the sound we know is 343. So we get h is 343 times the time for the sound. And now I have 1, 2, 3 equations with how many unknowns? TF, TS, and H. There's TF again, TS again, H again. So just 3 equations, 3 unknowns. We can solve that system of equations. And that's then what we proceed to do. So I'll just go ahead, come over here. Here's a system of equations. 3 equations, 3 unknowns, substitute and solve. So what I did, let's see. I went ahead and, let's see, we'll just do this. Went ahead and I set this h and this h then equal to each other. So 4.9 t final squared is 343 ts. And then ts, if I take this equation and rearrange, I'll get that TS is 2.5 minus TF. Plug that in where it says TS there. And now, look at that. It's an equation with just one unknown in it, TF. But we see that this is a TF squared term, and now I'm going to distribute that 343. I'll get a TF to the first power term and a constant term, which means we're going to have a quadratic to solve. Life's like that sometimes, right? But solving quadratics is pretty easy for my calculator to solve for me using solver program I like to use. And bam, you get the time for the rock to fall was 2.4166 seconds out of that total 2.5 seconds. We could subtract from 2.5 if we want to find the time for the sound to come up. But our purpose here, our goal here is to find that value for H. So I'm going to take that time and I plug the time for the rock to fall back into this equation for the rock falling. And I got that the depth of the well is 28.6 meters. So that's the depth of the well. And that's part A solved. Could I have done this in a more efficient way? My goal is to solve for H, so I probably shouldn't have eliminated H right away by setting the two H's equal to each other. It probably would have been more clever to substitute H over 343 in for TS there, and the root of H over 4.9 in for TF there, right? You know what I mean, for TS and TF. And then I would have had an equation that had just H in it right away. Would have had a nasty square root. I would have had to square both sides and clean it up probably, but whatever. And I could have made square root of H be the variable, I guess. I could have solved a quadratic. It would have been like a step cleaner, quicker doing it that way, but whatever. I found out the times too on the way. That's kind of cool. Okay, moving on, part B. So part B on this problem says, okay, if you ignore the fact that it takes time for the sound to come back, what percent error would you get? If you just assume that it was falling for that whole 2.5 seconds, how big of an error would that be? Calculate a percent error, that's not bad. Basically, you just say, hey, I want to find the percent error if we ignore the time it takes for the sound to rise. We treat situations if the rock just fell for the whole time. So what would we do? Well, we would just go ahead and assuming that the rock falls for the whole time, you would say delta x v naught equals 1 t squared for the falling rock. V naught is 0 because it's dropped. You just get that the depth there, that erroneous depth, is going to be 1/2 a times t squared, 1/2 g times t squared, calculates out to be 30.6 meters. So then you're like, okay, how big of a percent error is that? We know how to calculate a percent error. You take the value you get minus what the accepted true value is divided by the accepted true value. So see how much you're off by divided by the true amount times 100. So 30.6 divided by 28.6 over 28.6 because that's the accepted value. And we get 7% error. And you say 7%, is that significant? Now, how much error you're willing to accept, that's called your tolerance, how far things are allowed to be off. And for some things, you can't tolerate, hardly any error at all. Some things have to be super precise. Other things, you got a lot of leeway. So it kind of depends on a situation. The rule of thumb, the general rule that gets used in statistics is unless you have some other reason why you need to be extra precise or why it's not so important to be precise, what they usually use is 5% error to be like the boundary between something being significantly different or not significantly different. This is greater than 5%, so it's definitely a significant error if you ignore that time for the sound to rise back up. All right, which takes us to part C, and that is a little bit nastier to calculate. Part C asks, if the well was even deeper, would your percent error increase or decrease? And you can logic this out. Actually, it's not too bad to logic out. But if you want to mathematically prove it, it's a little rougher. So instead of answering the question, if it was even deeper, it'll be actually a little bit easier to think backwards and say, well, what if it was shallower? Like, what would that do for the error? So, this time for the sound to come back up, right? The time for the rock to fall, it's going way slower than this echo coming up, right? Than that sound coming up. And so think about the fact that if I back it up, that rock's going super slow to start with. And echo is like teeny fraction of the time, right? And almost all the time would be spent in the rock falling and almost nothing in that sound coming back up. So your percent error, you know what I mean, would become, ignoring the time the time to come back up is teeny. So you say almost, the error would be like almost nil, right? As you approach this thing, making this thing be like real like that. But the deeper you make it, right, then your error is just going to get bigger and bigger, ignoring this time that it's going to take for the sound to come up. So that's basically it. I mean, if you drop something like right away, almost all the time it's going to be it falling, and very little will be the echo coming back. So that's the deal. So the error is going to get bigger and bigger the deeper you make this well. But that's kind of, I don't know whether that's completely obvious logic or not. Not to me. Thinking about it, like I said, thinking about going backwards to what if it was really shallow, and you're like, oh well, gosh, this time it's almost nothing. Almost all the time is the falling. You're like, ignoring that time for it to go back up would be actually a reasonable approximation to make. But the deeper it makes, that time becomes more significant. So that's the deal there. But you know, things get weird when you talk about percentages. Like, okay, well, the absolute, I can see the magnitude of it's going to get bigger, but as a percentage, is it getting bigger? So here's the way that I did the calculation for it. Okay, I came up with this a couple of years ago and tried it out, and it seems to make a lot of sense to me. So here is the logic that I used in thinking through this. I said, all right, increase depth of the well, does the percent error increase or decrease? Here's my plan. What I'm going to do is I'm going to figure out a formula for the percent error as a function of the well depth. Okay, so big P, that's my percent error, and H is how deep the well is, right? And so I can see as I make the well deeper and deeper, as I increase H, we're going to say, what's going to happen to that percent error? What I'll do is I'll come up with a function for the percent error, and then I'll take the derivative of that function, right? So I'll get P prime of H, or dP dH is really what I'm doing, finding dP dH. And then if the derivative, I'll look at the sign of the derivative to tell whether it's increasing, decreasing, or constant as the depth is increased. So imagine, if you would, that I have some function, right? We'll say that this is the percent error, right, as a function of how deep the well is, right? So P is a function of H. And you say, if as I make it deeper and deeper, that error goes up and up and up, right? And maybe it's some kind of a curve, whatever. But the point is that as it's going up, if I measured like the slope of this, the slope would be positive, right? If the error is increasing. On the other hand, and if the slope is positive, that means when I take the derivative and I plot, you know, dP dH or whatever, or P prime, however you want to say it, versus H, that would give me positive values. My graph would be up here somewhere. If, on the other hand, that percent error as a function of H, if it was getting less and less as I made it deeper, then my slopes here are going to be negative slopes. And so then when I look at dP dH, right, or P prime, I'll have values that are down here. I'll have negative derivatives. So I'm going to just check the sign on the derivative. So first I got to come up with a function for the percent error in height, in depth, as I change that depth. So here's what I came up with. I'm going to say, okay, calling that depth H, you'll say there'll be the erroneous depth, right? Erroneous depth of the well. That's assuming that, ignoring the time for the sound to come up, minus the actual true depth divided by the true depth times 100. Okay, so that's my function. Now, let's see here. Finding that true depth, right? Well, if I could go ahead and say, well, of course, the total time is the time for the rock to fall and the sound to come up. The time for the rock to fall, that's going to be H is 1/2 GT final squared, right? Rearranging, time for the rock to fall is the root of 2H over G. Okay, this is from the kinematics equation, 1/2 AT squared plus V naught T. V naught T is 0, drops out. So 1/2 AT squared, right, is my delta X. And then the sound coming up, constant speed, is just velocity times time, but it's the time for the sound to rise. So time for the sound to rise is going to be that depth divided by the speed, right? Then we put those expressions for t into the total time equation. And that looks like that. And I'm going to square it, that total time, because I'm going to need it squared in just a minute, which means I got to FOIL out these two terms, and it looks nasty like that. Now, for the erroneous calculation, if it's falling, I just assume that total time, right, it was falling. And so to get that height, I would just take 1/2 g times the total time squared. See, that's why I needed that total time squared there. This is that v naught t plus 1/2 at squared, right? Assuming that we're dropping it and that all the time is in the fall. So that's it. So then I put this in terms of, you notice this equation is in terms, well, we'll talk about it in a second. So I get that like this and tidy it up a bit, and I get this for that erroneous depth that I get in terms of the real depth, and g, which is a constant, and vs, which is a constant. Do you see that? So the only variable in here is h. So I have he in terms of h. That was the point of all this exercise here. Put that in here where it says he. So here it is set in there. Conveniently, that h and that h, those terms cancel each other out. Now, all I've got left in here, there's h and constants, right? I'm going to go ahead, divide by h. I'm going to go and move that into each term, right? And I'm going to take that times 100 and distribute that to both terms. And I get this pink line here, right? Yeah. And now the only variable in here is h, right? I got h and I got the square root of h, right? And the rest of this is constants. Now I want to take the derivative, right? And see if the derivative is positive or negative at different depths. Well, it turns out taking the derivative of this expression is actually shockingly easy, because this is just a constant times h to the 1/2 power, and there's a constant times h to the first power. We're adding them, so it's going to be the sum rule. The derivative of the sum is sum of the derivatives. So I just have to take the derivative of this chunk and the derivative of this chunk and add them together. And then each of these chunks, this is just the power rule here, h to the 1/2 power times a constant. So I'm just going to kick out a 1/2 in front and drop the power here down to negative 1/2. This one is just a constant times h, so the h will drop out, it'll just be that constant. It's like a linear function. So taking the derivative with respect to h, bam, that's what we get. H to the negative 1/2 power, and this is just a constant term. Now, this is all positive, right? G is a positive 9.8. The speed of the sound squared, that's a positive. Again, positive, positive, positive. This is to the minus 1/2 power. That just means it's 1 over the square root of h, right? So you say, well, wait a minute. This derivative then, right? All tidied up here. I'm going to put that 1/2 in there. But can this be negative ever? This is never going to be negative, never going to be 0. There is no real value of h that can make this thing negative or 0. Also remember, h we defined as positive value. So the point is the slope is always positive, which means the slope of the percent error is positive. The percent error is just going to be increasing all the time as we make the well deeper and deeper. And so there it is, mathematically proven. Did you have to do this? Well, no. You could just think about it and recognize, I think sometimes going to like extremes, okay, let's make the depth of the well like practically nothing and look at it, and make it really infinite and think about what would happen. It's helpful for just seeing the answer. But it's nice to know that we can actually do the calculation, and it was cool to take a little bit of derivatives out for a spin too. That was kind of neat, and look at what's happening here. So there. Again, I would not expect you to derive all this. This is rougher than anything you would see on the AP exam, because the AP exam has to test your understanding of a whole lot of different things in a short period of time. This is a lot of math. And a little bit of physics applied, but mostly math. They would not make you grind through a calculation this long, because they don't have the time for that on the exam. So don't sweat it, but it's just kind of neat to see.